In this video, we're going to talk about forces and how it relates to motion. We can define a force as simply as a push or a pull. So even if I just push against this wall, I'm exerting a force, but obviously I'm not strong enough to push the wall over. So forces don't always create changes in motion. If a force does create a change in motion, we call that an unbalanced force. If there is no change in motion, we say there's balanced forces. For example, this baseball on the table right here, it's not changing its state of motion. There's balanced forces here between the force of gravity on the mass of the ball as well as the opposing force of the table restricting any further movement by the ball. If I give this ball an unbalanced force, I change its state of motion. Now the ball's in motion again. But the ball eventually comes to a stop after the sink stops its motion. Or you can think of it this way too. Notice how the ball slows down and comes to a stop. What brings that ball to a stop is friction. Friction is another type of force. There's what's called a coefficient of friction for every surface. Regardless of how smooth a surface is, it's going to have some level of friction. That friction is going to oppose any motion of an object. And that's what we're going to look at is the influence of forces on motion. The best way to think through this is examining Newton's three laws of motion. The first one being inertia. We often use inertia in our conversations and assessments and observations of car crashes. If you hit the brakes suddenly, the people in the car will continue in its previous state of motion. That's what inertia is. Whatever motion an object has, it wants to continue in that motion, speed and direction, until it's acted upon by an outside force, which is why we wear a seatbelt. In case of a car crash, upon a sudden crash or sudden stop, the seatbelt keeps us from continuing forward towards that direction of impact. I can simply model that using this water bottle. I can slide that water bottle. Notice how friction, the opposing force, brings it to a stop. If I add my hand here, why does the water bottle fall over? It's because it wants to continue in that state of motion, and my hand is creating the sudden stop. That's inertia. I can look at that again using this simple jar, 3x5 card, and penny. Right now that penny is at rest. If I suddenly quickly grab the 3x5 card, because the penny is already at rest, it wants to stay at rest, which is why it should fall into the jar, like so. Okay, I can model that again. You may have seen these videos where a magician or somebody pulls a tabletop off a table and all the glassware and plates are unchanged. So let's put some water in this jar to give it a little extra weight. Adding mass influences the amount of friction between the jar and the table. And again, the jar and the water is at rest. It wants to stay at rest. So if I suddenly pull this towel out from underneath it, it shouldn't go anywhere. Okay, and to make things a little dramatic, let's try an empty jar. And this is just simply modeling inertia. If something's at rest, it wants to stay at rest. Okay? So that's inertia. The second law of motion is looking at the relationship between force, mass, and acceleration. Simply put, if I exert a small force, if the mass remains constant with this baseball, if I exert a small force, there's a small acceleration. If I exert a larger force, there's more acceleration. And that relationship can be demonstrated mathematically using the formula force equals mass times acceleration. If I want to repeat this and have a larger, let's say basketball that's bigger and heavier, it's going to take a larger force to get it to accelerate at the same rate as the ball. Let me run a simple calculation. Force equals mass times acceleration. So if you're wondering what force would it take to get 100 or let's say 10 kilogram mass to accelerate at 10 meters per second, simple math is this times this is 100. And 1 kilogram times meter per second, we give that a new unit called newtons. So that would be 100 newtons of force. Okay, that's one way we could use the formula. I could do this again. If how much force would it take to, let's say, get a 100 kilogram mass to go the same acceleration? Well, now I just, you do your math here and you have 1,000 newtons. So what do you see here? It takes a larger force to get a larger mass to go the same acceleration. Let me model this again with these two motion carts. So the force involved here is just the tension of the rubber band. And as I pull these apart, the force that's going to cause these carts to move is the same because it's in the tension of the rubber band. When I let go, you can see we have a collision. And you can see we're not calculating the speed and the acceleration of the carts, but it's the same. However, as soon as I add weight to the cart, I pull these apart, the force on both is the same. What would we anticipate? Well, since the mass of the one with the baseball is much higher, it's going to have a smaller acceleration than the one with no weight. And you can see the mass of the cart makes a difference. And those are the relationships that we see in Newton's second law, F equals ma. Finally, the third one is looking at for every action there's an opposite and equal reaction. We see this in a humorous way when somebody is trying to step out of a canoe. As they step forward, they're exerting a force behind them, which the opposite reaction is that usually propels you forward. But since a canoe is in water and that's movable, when you step out of a canoe, it pushes the opposing force. The reaction is the canoe moving and you falling into the water instead of onto the dock. We see this with balloons. You fill up a balloon full of air, it builds up air pressure. As that air exits the balloon this way, that creates an opposing, opposite reaction of the balloon traveling in the opposite direction. You can see this in outer space as well. If you like hunting or you've used a gun, the recoil action of a gun is another example where there's a force exerted in one direction and there's an opposite and equal reactive force in the other direction. So that gives you an introduction to the three laws that Newton has identified with motion that work in normal situations here on Earth, as well as forces and how it impacts motion.